Welcome to TipsKnowLogy. In this video, we will be learning about serial communication. Computers transfer data in two ways. The first way is by parallel, and the second way is by serial. When we say parallel, it involves 8 or more lines. And when we say lines, it means wires or conductors or wire conductors. And these 8 or more lines are used to transfer data to a device. And this device where the data is being transferred to is only a few feet away. For serial, to transfer a device located many meters away, the serial method is used, and the data is sent 1 bit at a time. So you will see in this figure that in serial transfer, we have on the left the sender with a line and an arrow pointing to the receiver, and it's only a single line. Whereas for the parallel transfer, we have the sender on the left with 8 lines from D0 to D7 pointing to the right to the receiver. So this is like the block diagram for serial transfer, and this is the block diagram for a transfer or parallel transfer. So these are the basics of serial communication. Now at the transmitting end, the one that is transmitting, the byte of data must be converted to serial bits using parallel in serial out shift register. So at the receiving end, there is a serial in parallel out shift register to receive the serial data and group them together into a byte. When we say byte, it means 8 bits. When the distance is short, the digital signal can be transferred as it is on a simple wire and requires no modulation. So this means that if the distance is not far, so the digital signal can just be simply transferred as it is without any amplification or modulation. If data is to be transferred on the telephone line, then it must be converted from zeros and ones to audio tones. Now, these conversions from zeros and ones to audio tones is performed by a device which we call as modem. Modem means modulator, demodulator. It is a device used to convert from zeros and ones or digital signals to audio tones. Now, serial data communication uses 2 methods. The first method is what we call as the synchronous method, which transfers a block of data at a time, whereas an asynchronous method transfers a single byte at a time. When you say a single byte, it means 8 bits. Whereas when we say synchronous, again, the synchronous method transfers a group or a block of data at a time, whereas asynchronous will transfer a single byte at a time, not a group of bytes, but a single byte at a time. Now, it is possible to write software or a program to use either of these methods, but the programs can be difficult to do and it will take a long time. So there are special IC chips made by many manufacturers for serial communications. And we have here what we call as UART, which stands for Universal Asynchronous Receiver Transmitter. We also have what we call as USART, which means Universal Synchronous Asynchronous Receiver Transmitter. If the data can be transmitted and received, that is what we call as duplex transmission. If the data is only transmitted one way at a time, it is referred to as half duplex. Again, half duplex means data can only be transmitted or transferred or given to another receiver one way at a time. So that's what we call as half duplex. It could be from the transmitter here, you will see the half duplex from the transmitter to the receiver on the right, or from the transmitter on the right to the receiver on the left, but one way at a time. Now, if the data can go both ways at a time, it is what we call as full duplex. Example is the transmitter is going to the receiver here, and another transmitter on the right is going to the left. So they are doing this at the same time. That's what we call as full duplex. Now, a protocol is a set of rules agreed by both the sender and the receiver. And they talked about, or they agreed on how the data is packed, how many bits will be constituting a character. It means how many bits in a character. When will the data start or begin, and when will the data end? So this some sort of rules or set of rules of protocols will be agreed by both the sender and the receiver. So a protocol, again, is a set of rules agreed by the sender and the receiver on how the data is packed, how many bits will be in one character, and when will the data begin and end. Asynchronous serial data communication is widely used for character-oriented transmissions. And in each character, this is placed between start and stop bits. This is called the framing. It means that the data or the characters that you are transmitting is being placed in between another character. So there will be a start character and a stop, not character, I mean, there will be a start bit and there will be a stop bit. And that will envelope, or it will be like, we will know where's the start and where's the end. And this is what we call as framing. Block-oriented data transfers use the synchronous method. Now, the start bit is always 1 bit, but the stop bit can be 1 bit or it can also be 2 bits. Now, you will see in this diagram or picture or image that the ASCII character A, which is actually 01000001 in binary, is being transmitted. So you will notice that the original character that we want to transfer is letter A, and it is 01000001. And you will see here that when it is a 0, you just need to put the signal down here, and when it is a 1, make a signal up. And this represents our character A. But you will notice on the right side that there's what we call as a mark, and this mark or signal 1 is included in our sending of message or the character A. So it means that the character A will not be the only characters or the only bits that will be transmitted. There's also a 1 and a 0 here on the right side. This is mark, and this is what we call as the start bit. And this goes out first. So this start bit signals the start of the transferring of data, and so it will be taking the data here. And then it will be, when it reaches the 8th data or D7, we will be having a stop bit here, and this will go out last. And then it will be, there will be a space. Now the low is referred to as space, and the high is referred to as mark. So we'll have mark, start bit, and then our characters, and then stop bit, and then space. So this is how the characters are being sent. For example, character A. Now, if we are sending character B, then it will not be these characters or these bits. It will be 01000010. That's the only difference if it is letter B. Letter C, letter D, and so on up to letter Z, or any other character, as long as it can be represented by a binary digit or 8 binary digits. So this is how the start bit and the stop bit is being used. So it's being placed here on the right side and here on the left side. And before the start bit, let's say there's nothing there, then it will be on the mark or a 1. And after the stop bit, we have here what we call as a space. Now, due to the extended ASCII characters, 8-bit ASCII data is common, but in older systems, the ASCII characters is only 7 bits. Now, in modern personal computers, the use of one stop bit is standard. In older systems, due to the slowness of the receiving mechanical device, 2 stop bits were used before to give the device enough time to organize itself before sending the data or the bytes. Now, assuming that we are transferring a text file of ASCII characters using one stop bit, we will have a total of 10 bits for each character. And as you can see here, we have 8 binary digits plus the start bit, that would be 9, and then plus the stop bit, that will be 10. So out of 8 characters that we need to send, we will put 2 extra binary digits for the start and stop bits. Then we will be having a total of 10 bits to be sent. So we just need to send 8, but we will be sending 10 because of the start and the stop bit. And because of that, instead of sending 8, we send 10. Then we will have an overhead. Overhead is like an extra bits that we have to put. And if you calculate 2 out of 8 is like 25% of 8 bits. So 25% overhead will be there. The rate of data transfer in serial data communication is given in bits per second. So when we say BPS or bits per second, this is the rate of data transfer in serial data communication. Another term that we use is for BPS is what we call as the baud rate. And the baud rate refers to the number of times that the signal will change per second. So again, baud rate is defined as the number of signal changes per second. Now in modems, there are occasions when a single change of data transfers several bits of data. And as far as the conductor wire is concerned, the baud rate and the bits per seconds are the same. And we use the terms interchangeably. And it means we don't really focus on whether it's baud rate or BPS, because as far as the conductor wire is concerned, it is basically the same. But again, when we say BPS, this is the bits per second, or the rate of data transfers in serial data communication, while baud rate is the number of signal changes per second. Now, to allow transfer between the PC or the personal computer and an 8051 system without any error, we must make sure that the baud rate of the 8051 system matches the baud rate of the personal computer's communication port. So these are the personal computer baud rates. We have here 110 up to a 19,200. So these baud rates are supported by 486 Pentium IBM PC BIOS. BIOS means Basic Input Output System. As you can see here, like this one, 9600. If we are using Arduino and we are using the serial monitor, you will notice that we are choosing usually the 9600 baud rate for our serial monitor. Now, with the crystal frequency of 11.0592 megahertz, find the TH1 value needed to have the following baud rates: A, 9,600, B, 2,400, C, 1,200. The solution to this is that we have to divide the crystal frequency given, 11.0592, by 12. So the machine cycle frequency of 8051 will be equal to 11.0592 megahertz divided by 12. We will have an answer in megahertz converted to kilohertz. That will be 921.6 kilohertz. And then after that, we need to divide this 921.6 kilohertz by 32. and we will be getting 28,800 hertz, which is the frequency by UART to timer 1 to set the baud rate. So this is the procedure. Again, divide the frequency given, 11.0592 by 12, and then after getting the answer, whether it's megahertz or kilohertz, divide it by 32, and you will get the answer for our machine cycle frequency. And after that, then we will be dividing the answer, for example, 28,800 hertz divided by 3 for letter A, which is 9,600. And then for 2,400, we have to divide it by 12. And for 1,200, we have to divide it by 24. Now, you might wonder why will we divide it by 3, by 12, and 24? Because it's simply given, assigned to the baud rates of 9,600. As you can see in our example here, that the 9,600 must be 3, and then 4,800, 6, and then 2,400, 12, and 1,200 is 24. So in these examples, the number -3 is FD in hexa, F4 for the 12, and E8 for the 24. So these are all loaded into the TH1. Now take note that when we divide 1 over 12 of the crystal frequency by 32, this is the default value upon activation of the 8051 reset pin. So this is a constant value that we are using. Now, the data transfer rate of a given computer system depends on the communication ports that is included into that system. For example, for the IBM or International Business Machines personal computer XT, it could transfer data at the rate of 100 to 9,600 bits per second. So it means that there's a particular assigned BPS for a particular system of a that we are using. For example, for IBM PCXT, we can only transfer data from 100 to 9,600 bits per second. For Pentium-based personal computers, we can transfer data at a rate of as high as 56K BPS. Take note that K here is not 1,000, it means 1,024. So 56 multiplied to 1,024, although we can say it's approximately 1,000. So 56 kilobits per second for Pentium. And then in asynchronous serial data communication, the baud rate is limited only to a maximum of 100 kilobits per second. Now, moving on with some standards like the RS232 standard. This standard was set by the EIA in 1960. EIA stands for Electronics Industries Association. So in RS232, a 1 is represented by -3 up to a maximum of -25 volts, while a 0 bit is +3 up to approximately +25 volts. In other words, whenever we have a 1, digital 1, we are using -3 to -25 volts. And when we have a 0 bit or a digital 0, we are actually using a +3 volts up to +25 volts. So it makes the -3 to +3 undefined. Now, for RS232DB25 pins, like this one in the diagram, you will see that it has number 1 up to number 25. And all of these pins have some description, like I put circles here on the most commonly used here, or the most important there, or compared with other RS23225 pins. At least we know this. We have the number 1, protective ground, the transmitted data, received data, request to send, clear to send, data set ready. We also have here the data carrier detect. Of course, we have the signal ground here. We have 9 or 10 reserved for data testing. 11 unassigned, 12 is secondary data carrier detect, 13 is secondary clear to send, and so on down to number 25. This is what the RS232DB25 pins look like. And you will notice that if you will look closely, this is similar to what we used before for our printers when we are connecting our printers, the old printers that we are using before to our computer. Now again, this is the actual picture of a male and female RS232 connector and the one we are connecting with. And you will see that this is the pin out for the male. And you will also see that, of course, there's a female pins here or plugs where you will put the male pins. So this is number one. This is another way just to represent the same as what we have shown here in the previous slide. Now, since not all pins are used in personal computer cables, IBM introduced the DB9 version of the serial I/O standard. So this is what we call as RS232 connector DB9, and you will notice that compared with the previous one, which has 25 pins, this one only has a 1 to 9, or we have 9 pins. And the number 1 to number 9 are designated here, which with its description. 1 being the data carrier detect, received data for number 2, transmitted data for number 3, data terminal ready for 4, signal ground for number 5. And you will notice that on the previous example, the number 5 here is not the ground. Instead, the number 7 is the signal ground for the DB25 pins. And for DB9, the signal ground is on number 5. The number 6 is dataset ready. Number 7 is request to send. Number 8 is clear to send. And number 9 is for the ring indicator or RI. Again, this is the pin out in a different view. So you will see here that at the top we have 5 pins, and then at the bottom these are the 4 pins at the bottom. These are the male pins, and this is the female where we put these male pins. Now, the current terminology classifies data communication equipment as DTE or data terminal equipment. This refers to terminal and computers that send and receive data. So again, DTE stands for data terminal equipment. Now, DCE stands for data communication equipment, and this refers to communication equipment such as the modem. Again, modem stands for modulator, demodulator. And the simplest connection between a PC or personal computer and a microcontroller requires a minimum of 3 pins. So we need the TXD, the RXD, and the ground at least. So again, we need at least 3 minimum pins like TXD, RXD, and the ground to connect to do our connection between the PC and the microcontroller. Now, again, these are the meaning of DTR, data terminal ready. When terminal is turned on, it sends out signal DTR to indicate that it is ready for communication. DSR or dataset ready, when the DCE is turned on and has gone through the self-test, it asserts this DSR to indicate that it is ready to communicate. RTS means request to send, and when the DTE device has a byte to transmit, it asserts or calls RTS to signal the modem that it has a byte of data to transmit. CTS stands for clear to send, and this time when the modem has room for storing the data it is to receive, it will send out signal CTS to the DTE to indicate that it can receive the data now. The DCD stands for data carrier detect, and the modem asserts or calls the signal DCD or gives the signal DCD to inform the DTE that a valid carrier has been detected and that contact between it and the other modem is already established. The ring indicator is an output from the modem and an input to a PC, which indicates that the telephone is ringing. And it goes on and off in asynchronous with the ringing sound. Now, let's have some examples of transmitting and receiving data using C language. Let's write a C program for 8051 to transfer the letter A serially at 4,800 baud continuously. And let's use 8-bit data and 1 stop bit. So you will see in the program that we have in the first line the include reg51.h header file. We have then the void main void followed by tmod 0x20. This means mode 2, mode 0. Mode 2 for timer 1 and mode 0 for timer 0. So we will just be using timer 1, mode 2. And then we have th1 equal to 0x fa. This is for the 4,800 baud rate. So if we go back here, let's look at the 4,800 baud rate. You will see here 4,800 baud rate. We are using FA. In other words, we can also use 9,600, 2,400, or 1,200. But if we do that, we will be using FD, F4, and then E8. So going back to the program, that's what we mean by this FA. So if you're given another baud rate here, not 4,800, it can be any of the following. It can be 9,600, 2,400, or 1,200. Then we have the Escon equal to 0x50, and then we will have TR1 equals 1, and then we will put here while 1, open bracket, SBuff, letter A, this is to place the value in the buffer, and then while TI equals 0, semicolon, do nothing, then TI is equal to 0. So if I change this letter to letter B or letter C, it simply means you will just change SBuff from letter A here to letter B or whatever character you want to put here. It's not necessary to just put letter A to Z. We can use any character that is available on the keyboard to be placed here. Now, with a crystal frequency of 11.0592, I think this is the same example that was given to you before. So I'll just move ahead to the next slide. Now, by the way, the Escon Register, talking about it, is an 8-bit register. And this is used to program the start bit, the stop bit, and the data bits for data framing, among other things. But you will particularly look at TI here. This is the transmit interrupt flag. So the TI here is the transmit interrupt flag. So in other words, when we say 0x50, you're actually putting 5, hexa 5, which is 0, 1, 1, 0. And the 0 number here is hexa 0. So in binary, it's 0, 0, 0, 0. Again, when you say 50, it's like 0, 1, 1, 0, and then 0, 0, 0, 0. And that will be the values of this Escon register. So 0, 1, 1, 0, 0, 0, 0, 0. That's what will happen. And by the way, the TI here is the transmit interrupt flag. And if in your program, you will notice here that there's a while TI equals 0, while TI equals 0. So that's the TI that we are talking about there, the transmit interrupt flag. And this is set by the hardware automatically at the begin of the stop bit mode 1. And this will be cleared by the software or by the program. That's why we have here TI equals 0 to clear it. Okay, going back to our example. So let's have another one, SBuff. When we say SBuff, this is an 8-bit register used solely for serial communication. It means it has no other use but for serial communication. For a byte data to be transferred using the TXD line, it must be placed in the SBUF register. And the moment a byte is written into the SBUF, it is framed with the start and stop bits and transferred serially via the TXD line. Now, the SBUF holds the byte of data when it is received by 8051 RXD line. And when the bits are received serially via RXD, the 8051 deframes it by eliminating the stop and start bits, making a byte out of the data received and then placing it in SBUF. Let's take a look on the SBUF again here. You will see here we just put SBUF equals A if we are transferring the letter A. If it is letter B, we put SBUF equals B. So again, buff means buffer. Now the TI, which is actually on the Escon .1, transmit interrupt flag is the meaning of TI. This is set again by the hardware at the beginning of the stop bit mode 1 and is cleared by the program or software. Now let's have another example here of an 8051C program that will transfer the message yes serially at a rate of 9600 baud rate, 8-bit data, and 1 stop bit, and do this continuously. So you will notice here that we have the letters Y, E, and S here. In other words, if I will be sending the message no, then I'll just put here 30XN and then 30XO, and I will cancel this third line here, while everything will be the same. Now, you will also take note that the baud rate is 9600, and unlike before that we are used FA, this time we are using FD for our TH1. So again, if you forgot about it, this is the 9600 and the TH1 is supposed to have FD. That's why here we have TH1 equal to 0x FD. Now we also have here T mod is equal to 0x20 because we are supposed to use timer 1 mode 2, although it was not given in this problem. Let's use timer 1 mode 2. And then we declared a function here which is called SERTX, SER or serial TX unsigned char. This is declared here because your function is down here at the bottom of main. So what's inside here? We have SBUF equals to X. By the way, the value X is a character and it will be like the receiver of the character that is sent by the SERTX function. So when you say SERTXY, it's actually calling the SERTX function here, and at the same time it is passing the letter Y to the variable character X here, to the unsigned character X here. So when you say serial TXY, the serial TX function here will run, and before it runs, it will take or accept the value of letter Y to X. Therefore, the SBUF will be letter Y, and this will be while T1 equals 0 true. It will wait until it is transmitted, and after being transmitted, then it will get out of that and it will go back to the main function. And it will repeat the process for letter E and letter S. So that's it for our serial communication video tutorial for today, and I hope you like the video and please share it, and I hope also that you will be subscribing to ERC TipsKnowLogy towards our goal of having 1,000 subscribers. Please help the channel to grow and to reach more people. Thank you so much.